So the subject is faster objects and arrays. Hopefully you're in the right room. What this really is about is trying to address what I believe is the last inherent speed difference between Java and C-based languages. That's not to say it's the last difference, but it's the last inherent one. And we'll get into why it's inherent and what we can do to address it. The content I'm going to describe is under a project we call org.ObjectLayout or objectlayout.org. If you like the class path, it's org first. And you could go to the website, look at it. You can do it live if you want. Might find some interesting things as we go. I'm going to describe what it is, status of where it is. This presentation, I kind of put it together first for the most recent Java Language Summit, and we are trying to advocate for this to become part of a Java standard version in some future point. Maybe 9, maybe 10, maybe we'll see. Anyway, let me start by introducing myself. My name is Gil Tene. How many of you have seen any of my talks before? Okay, so some of you will have seen this slide many times. I really need a new one, but I'll quickly describe who I am. I'm the CTO of Azul Systems. One of the things people know me for is that I've been working on garbage collection for a while now, about 13 years. And when I say working on garbage collection, we think of it as kind of think different garbage collection. This is what the industry is doing about garbage collection. We went the other way. Rather than incrementally solving things and improving them slowly and maybe reducing the pressure here and there, we just said, you know, how about if we just solve the damn problem? And we did. So we believe garbage collection is simply a solved problem. We have a working shipping solution. We think others will also solve it over the coming decade. It takes a little work. But when I say solved, I mean you don't have to worry about it anymore. You don't have to worry about pauses. You don't have to worry about not having too many objects or allocating too fast. It's cool. Anyway, that's products. That's what we actually do. If you're interested, we have a booth outside, but that's not what the talk is for. Just some evidence that I actually do this stuff. This is me working on garbage collection in my kitchen. That contraption over there, that's a trash compactor. And I apologize to those guys that have seen this 17 times already. It's a trash compactor. The job of a trash compactor, how many of you have a trash compactor? How many of you know somebody who has a trash compactor? Douchebags. Yeah. Well, I have one. I'm lazy. The job of a trash compactor is to perform minor garbage collections during the week, delaying the full GC where you take the bag out to the weekend. And when it performs well and it's well tuned, it'll do that very well. But in this case, it was broken. Fragments were coming out the back. The compaction function wasn't working perfectly. I had to debug it. That actually happened, by the way. I just thought it'd be funny to take a picture with a garbage collection theory book when I did that. Probably the main data point in this picture is it was taken in 2004. So that's just to prove you I've been doing this or thinking it's funny for more than a decade. Anyway, I've built a lot of things. Everything from virtual machines to physical machines, actually designing CPUs and hardware. Built operating systems and drivers and firewalls and switches and big management systems for millions of subscribers built in Java. Which is kind of how I fell into this field. Another pet peeve or hobby of mine is to actually go around depressing people about the state of their latency measurement. I have a whole set of talks on that and actually a full workshop on Thursday if you really want to get depressed or learn how to depress other people or just point a finger at them and laugh. But it's just an interesting subject. You know, latency measurement, good, bad, how are you doing it, and measuring something other than noise. But this is not what we're going to talk about today. We're going to talk about org.ObjectLayout. So what is this? The focus of org.ObjectLayout is to match the raw speed benefits, the raw benefits, that C-based languages can commonly get and commonly use in Java. And we're talking about the layout-related benefits. I'll be specific as we go. We want to expose those benefits in Java for plain Java objects, for regular Java objects, for all Java objects that you have. We don't want to create a new type. We don't want you to go to an off-heap location. We don't want you to start inheriting from X or not be able to do Y. If it's a POJO, we want to be able to lay it out efficiently and deal with it efficiently, similarly to how C does the same. The focus is very narrow and very specific. We are focusing on speed for regular Java objects on the heap. That's a mantra I'll keep repeating, okay? It is not any of these things. It is not about improved footprint. We are not trying to reduce the footprint of anything. I told you I think garbage collection is a solved problem, right? I actually think our problem is we're not using enough memory in machines. We have machines with hundreds of gigabits, and we think 10 gigabyte is a small number, is a big number. So I don't have a problem with waste, I have a problem with speed. We want to address speed. If footprint addresses speed, that's a valid concern, but memory is cheap. And if you want to solve it, but not as part of this. Off-heap, great things about off-heap. For example, you might want to talk to something that's not Java, or maybe you have a garbage collection that doesn't work right, so you want to get objects out of its way. But it's just not related to what we're doing here. And immutability, good or bad, is again orthogonal. We just don't care. Immutable objects are great, and so are mutable objects. And we want all objects to be able to benefit from the speed we're talking about. All these are simply orthogonal concerns. They're not good or bad. I just don't care about them. So keep that in mind as we go through this. The next slide or two is going to focus on what object layout isn't. And there's a reason for that. Every time I mention it to people, they say, value types or packed objects. So it's not. The relationship between object layout and value types is none. The relationship between object layout and packed objects, or JNR, I think there was a JNR talk or something mentioning JNR earlier. I didn't actually attend it, but Charlie's here, right? Somewhere. And it's none. There are good reasons to have those. Hopefully they'll work through exactly what they need to do, show up in the Java version. This is not an overlap at all. The laser focuses on a different problem. Neither one of those things is focusing on speed for regular Java objects on the heap. There's no conflict with the other things. So this is not instead, this is not don't do that, do this. This is we should do this anyway, and other things are good ideas too. There is a tiny bit of overlap. It's the same kind of overlap you have between an array list and a hash map. Both of them are good bags to put things in. But if you had both of them, if you only had one of them, you'd have a problem. Right? There's a good use for this, a good use for that. Use it where the fit is. One more pictorial way of looking at this is here's the space in a kind of a Venn chart. Value types, packed objects, and object layout. Value types are about on-heap things. You know, codes like a class, acts like an int, or, sorry, whatever. But you get the nice immutable nature for small objects, probably small objects. Great for on-stack things. I can't tell you how many times I really wanted a value type instead of having to do weird things, packing things, or creating an object just to pass a tuple. So return values, passing parameters are great for that, for a lot of on-stack, on-thread things, maybe for some thread local things. In the heap, most likely you're going to see value types that are handed between threads be inflated, meaning basically wrapped types that are as fat as a regular object, boxed if you'd like. But we'll see how those mature. They're really useful. I really want them. I wish they were in Java 9. Probably not going to be there. Well, we know it's not going to be there, but hopefully in Java 10. If we look at packed objects, first and foremost, this is an IBM initiative, and there's some other derivatives of it. First and foremost, it's about a precise control of layout. And there's a really good reason to precisely control layout when you talk to things that are not Java. If you're looking at a TCP header, the bytes go in certain places. If you call a native API, and that native API has a C struct as a parameter, you need to get the bits right in the struct, or you're not passing the parameters right. And the glue logic that we have today around those things is very cumbersome, especially if we want speed. So off-heap exact layout for things that create structural things, not just buckets of bits, are important. And if you look at what people actually do about that, they usually create some big byte array off heap, and then they create light or flyweight objects that kind of scroll over them and look like objects, but kind of know what bytes to do what with. We all do that over and over and over again. A library that would do it and standardize would be very useful. I would very much like to see something in that space evolve, and I hope the JNR will do it and learn a lot from Packed Object. It's about sharing information with non-Java stuff. Primary thing is off-heap sharing with non-Java. You can't let the JVM layout stuff if other people want to know what it's like. Object layout, speed for objects on the heap, regular Java objects. Last way to look at this is value types is going to be about new code. A value type is a class that does not behave quite like an object. There are things you cannot do with it. For example, you can't get an identity hash code. You can't lock it. You can't synchronize on it, which means that you can't give it to code that thinks this is an object. It is dangerous to do so. So value types are going to be very useful for new code that is written for value types. I want that. Similarly, packed objects are inherited from a new base type that is not an object, so clearly only for things that have that code. In contrast, object layout is designed to address any existing constructible Java object in the world. That you can take objects that participate in some of these and hand them around to 6-year-old code because it knows what to do with them. So the scope of what we're going to touch is dramatically bigger, especially if you look at the ecosystem as far as what we can interact with. Okay, enough about what it's not. Let's look at what it is and why. The origin of this actually started from an argument. An argument between me and Martin Thompson. Is Martin here? He's seen this 3 times, so he doesn't need to be here. He reminded me that the argument lasted until 3 a.m., sitting in a car outside of his hotel. The sides of the argument look like this. On the one side, there's we need structs in Java. We're sick and tired of building these weird arrays and running these weird things on top of them. It's ugly, ugly code, and it's buggy, and why do we have to do it? And look at what all the unsafe stuff you guys make us do. Can't we just have structs in the language, right? And there's good, reasonable drive there. The other side is to say, we don't need anything new in the language. We already have structs. We have better than structs. They're called objects. They can do everything a struct can do and more. So let's look at what's missing, what you're actually trying to achieve, and see if we can achieve it within the thing we already have. And that's what object layout really is attempting to do. To settle this, we said, you know what, let's just go start coding it up and see what happens, and that's where the project came from. So Martin and I both started coding StructuredArray, for example, to see if we can capture the things right. As we were doing this, we realized that what we're actually doing is trying to capture enabling limitations. And I'll explain what that is in a couple of slides, but it's the semantics that we're trying to capture, not the code, not the syntax or anything else, but the semantics that allow things to be fast. And capturing the enabling semantic limitation is the key thing in every one of the constructs we'll have here. So when you think of this from a design perspective, don't just look at what these classes do, but you can also look at this as a development exercise. If you were designing something new that you wanted to architecturally affect things, maybe affect the JDK in the future, you can look at this for some, hopefully, good lessons. So where does the speed that we want come from? Why does let this C have it and Java don't? It doesn't have it. C's layout benefits really come from 2 key things. The first one is something we call dead reckoning. Dead reckoning is the ability to get to something in memory from the address of a base of something without too many data dereferences in the middle. For example, if I have an array of structs in C, and each struct has 3 fields, X, Y, Z, and I want to get to element number 19, field Y. In C, if I take the base of the array, I can do math and figure out the memory location of Y in element 19 without looking anything else in memory. So taking this, computing the address goes straight there. That's dead reckoning. As opposed to look up element 19, follow, and then get there. So dead reckoning is about getting straight to the memory zone you want without jumping through other data dependence things. That gives you obvious speed, especially given modern CPU pipelines that are really good at running through a lot of math well with superscalar things, but are really bad at saying, well, I don't know where to go next, so let's wait until I compute that, and then I'll go the next step and the next phase. It breaks pipelines to have data-dependent operations. You're serializing an operation in a CPU. The other one is streaming. Streaming is really about exchanging latency and bandwidth. CPUs have tons of bandwidth. Memory caches have tons of bandwidth. The problem we have is that the latency to the memory is fairly high. When we miss in the cache, when we go to a place we haven't gone to before, it takes hundreds of cycles to do. And if we hit an L1 cache, it's 1-2 cycles effectively. Now, because of that gap, we like to prefetch data. If we know what we might need to access and the CPU can get it for us, then it's going to spend bandwidth getting it before we need it, and then it'll be there when we need it. Now, sometimes that's wasteful. Sometimes it's getting stuff we don't really need because it's guessing. But it gets to burn that bandwidth in order to improve our latency. Streaming is extremely powerful when you have constant stride access. You're going through an array looking at field Y of everything, or at all the fields of everything. So if you look at the addresses you're accessing in memory, there's a pattern to them. Modern CPUs have hardware prefetchers that are sitting there actively looking at the pattern of your memory accesses, saying, oh, you did this and this and that. There's a pattern. Let's keep going. And they get ahead of you and they prefetch for you. And if they do it well, you miss in the cache, but you don't wait for the miss because the miss happened before you ever got there. It's extremely powerful. It's an order of magnitude improvement on accessing through things. But it only is there if you're accessing in a pattern. The reason arrays of structs are very powerful for streaming is because they're laid out flat. So if you access all the elements, you are accessing memory in a pattern. If things were jumbled up, there would not be a pattern, and when we get to element 19, after we've been to element 18, we don't know where that is, because we can't dead reckon into it anyway. These two things are with a lot of speed, a lot of speed. These two things are hard to do in Java. So let's look at the enabling, or the speed enabling limitations, and look at specifically what the semantics are that make it possible to achieve these with an array of struct. To do that, we should just compare the array in Java and the array in C. We have an object array in Java. That's the only way we can have an array of things that are not just a primitive field. And we have an array of struct in C. Those are the syntaxes. So in Java, an array of object is a mutable construct. Mutable because I can replace what element 17 is anytime I want. So element 17 was this, and later it's that. So I can mutate the array. And it's an array of same base type objects. The base type may be object, or suppose I have an array of points. It could be an array of point or any subclass of point. The reason that's important is because the elements don't have the same size. They might or might not have the same size. These two things in combination are a problem. If we compare them to C, in C, an array of struct is an immutable. Funny to see immutable in C, right? But it's an immutable construct of exact same type things. Two very powerful qualities. Immutable because it's a flat array of structures. Element 17 is element 17. You can't change who it is. You can go mess with its contents, but you can't change which element is number 17. And it's same type because it's a struct, and it's the same struct, right? That's trivial. But that means it's the same size. Now, these two qualities are the things that enable or break speed. Because mutability and non-same typeness individually break both qualities of dead reckoning and streaming. You cannot dead reckon or stream into a mutable array or into a non-same type array. Why? Well, if I can replace element 17 in the array, then by definition, there's no way to know what that is given the array address. I can't take array address and know which 17 is with math. I need to look at what you did to mess with it. That's a required dereference. That's no dead reckoning, right? Similarly, if I can replace them, then they're not going to be in order in memory. I might get lucky, and sometimes they're in order, but they're going to get shuffled, especially when you garbage collect and move things around. Separately, The non-same size individually, without the mutability, even ruins things, because if each one could be a different size, there is no math for what number 17 is, right? There are different lengths on the way to number 17, so I need to figure them out. And similarly, if they're not the same size, my nice equal stripe will break too, because I'll be hopping in different sizes every time, and the prefetchers won't guess what. Problem. Anyway, we need to eliminate both of these qualities in order to gain the speed that C has. And that's what structured array, one of the forms and classes in ObjectLayout does. Structured array is simply a collection that says, I need those qualities. So it's an immutable collection, meaning it starts and there's stuff in it and you can't put anything in it. Whatever is there at the start stays, of exact same type objects. You can't put objects of different types, simply because you can't put. You say, I need 100 of this, and that's what you have. You can't change that later. That's the capturing of the semantics. Now, when we look at the target forms, we have three key target forms in C that we're trying to emulate. The first one is an array of structs. We just spent some time talking about it. The second one is a struct inside a struct. And this is the C syntax for defining them. So the struct with the struct inside rather than the struct you point to. Now the nice thing is those two compose well together because you have an array of structs that have structs inside, and then you've got multiple dereferences you've saved. And then the last one that's very interesting is a struct with an array dangling off the end. A variable size array dangling off the end. That's very commonly used in communication. Messages with headers, payload and header, that kind of stuff. It's very common to see that. In C, it's very common to have that flat. You malloc the entire thing and you have a struct at the beginning and the rest is an array of bytes or ints or longs or whatever it is. Those three things are very useful. Each one of them gives you either dead reckoning or stringing or both. None of these can be replicated for speed today in Java. It is possible to emulate the function of them easily, but each emulation method you have cannot match either stringing or dead reckoning speeds in Java. It's inherent to how the JVM lays out things and what the semantics are. And that's what we want to fix. We want to remove the inherent quality here. So the starting point here is to say we want to capture the semantics that enable the speed. And the theory is that we can do this with no language changes at all. And we can capture them in a way that lets us take plain vanilla Java classes that run on any JDK, function on any JDK. You don't have to have a special environment to run them, but they're not going to run any faster on any JDK. It's just that you can have future JDKs, recognize what this is, understand the semantics, and realize that they can optimize it because the semantics enable the optimization. So knowing that this is immutable and same type, you can actually lay it out flat because they are allowed to. And as a result, you can actually do all the optimization C naturally does. The difference between what we call vanilla and what we call intrinsified, which is the optimized version, has to be speed and only speed. We do not want to have any way to write something that only works in intrinsified, only works or behaves differently between the two. That's a core requirement of this. Now, why did we choose these? Partly because we're thinking forward and saying we want to get this into the language, or sorry, we're not changing the language, into a future version of Java, and we want to make it happen in a less friction way or the best possible way, low risk way. And in doing that, we wanted to emulate successful things. There's an example of an extremely successful external contribution to Java, the most successful in history, and it's Java util concurrent. Java util concurrent was not developed by Sun, Oracle. It was developed outside by Doug Lee at Uni Oswego. How many of you had used Java util concurrent before it was Java util concurrent? Uni Oswego classes, right? So the way it was built is there was this class library and it captured the semantics for fast concurrent operations. The semantics that define what they are, that would enable the speed or the implementation. There were no language changes, no JVM changes needed to run that code. It ran on existing JVMs. Now, notice that there is still not language support for Java util concurrent. It's purely a set of classes. We might get some support in Java 9 with .atomic or .volatile. Now, the implementation in vanilla runs on multiple JDKs, but it may be slow. For example, you can emulate an atomic integer, compare and swap, or compare and set with a synchronized block. It won't be fast, but it'll work. You then have JDKs improved to recognize what that is and not do it with a synchronized block, but do it with a single instruction on a CPU and intrinsify it. And you move it into the JDK and the Java namespace so that it'll be locked down there and JDKs can safely know what it is, rather than some, oh, I think that random third-party library I just loaded has these semantics. I hope the next version does too. If it's in the Java namespace, then it's specified. You know exactly what it will do. You can replace the implementation. So let's look at the forms that we talked about and zoom into one of them, arrays and structs. Structured array is simple. It's a collection of type T, and it happens to be arranged like an array. You have a get by index, you get an object out of it. That's the API, the simple API to it, right? There is no put, remember? It's immutable and you can't replace elements, and to make it, you have to use a factory. For example, here, we're making an array with 100 objects of some class, some class.class, right? That's how you make one of these. All the elements are created, instantiated, and constructed when you made this. So there'll be 100 constructor calls when you do this because there's 100 objects being constructed. Right? And we support all kinds of interesting constructor forms because if you have to create all the stuff at the beginning and we want to support any constructible Java object, we can't just say the ones with default constructors, which, that's how the default constructor would be. You can get into some interesting complex things. So take as an example, suppose you have a class like this. Class doof, and it's got an internal final field. You have to initialize as a constructor, can't touch it later, and that final field is support to somehow indicate my index in something bigger. Why? Because that's what I chose here. Suppose I want to create an array with 8 elements of that. What I need to do is say which constructor I want to use. That's in Java how to say I need to use that constructor. And this is how you make the array. So I'm making an array of, that should be doof rather than my member object. Sorry for the typo. And see that lambda expression there? You don't have to use a lambda expression, but it's a perfect fit here where I say, for this context, create a new constructor and arguments with that constructor, and the parameter is actually the index into the array. So each element will get a separate parameter that depends on the context of where you are in the array. That's an example of a fairly complex interaction with the constructor, but it goes to that level. You don't have to do these unless you need that context. It's much simpler if you don't, but we needed to enable that kind of stuff in order to support arbitrary object membership in this collection. Liveness is a very interesting quality here. What we found when we started working on this is that we looked at this as something that other people have already done. Arrays or big objects with a reference to the middle of them because they're flat, and you want to give people a reference and they can hold it. And we looked at what other runtimes do, and invariably what they all do is there's this container thing and you point to the middle of it, and pointing to the middle of it keeps the outside alive. And we started down that path, saying, okay, if you have a live member of a structured array, then the structured array is alive by implication. And we worked down to see, okay, what would we need to do that? How do we support it in a runtime and a garbage collector is what needs to change. And this is doable because other runtimes do it, but it's kind of complex to change what Java does to do that. And about a month into this, one of our key GC guys, said, remind me again why we're doing this. Remember, there's a complexity should make you rethink the thing. So why are we trying to keep the container alive when we point to the member? Why do other people do it? Well, the reason other people do it is if you point to a field in an object, a field doesn't live by itself. If you point to a member of an array that's a struct, not an object, a struct doesn't live by itself. It doesn't have liveness. So what you're actually doing is keeping alive the closest thing that contains it that has liveness, which is why others chose that. But we have proper Java objects. These things that we put in the collection are regular Java objects. They don't need somebody else to keep them alive. They have liveness. If somebody pumps them, they're alive. If not, they're not. And with that, it was sort of a whole bunch of things that completely eliminated this work. The work actually became much, much easier to intrinsify, and we found that it's very, very natural. So StructuredArray is just an idiomatic Java collection. You already know how it behaves. Are there any other collections that you use where when you put something in it, the collection stays alive? If you put something in a hash map, that doesn't keep the hash map alive, or the array list alive, or the Bitbucket alive, whatever it is you're doing. If it's alive, it's alive. If it's not, it's not. And if the object is alive, it can stay alive even if the collection is gone. That's normal idiomatic Java. You don't even think about it. That's natural. So StructuredArray is the same. Now, under the hood, implementations are going to need to do nice tricks. If we want to optimize this, then yes, we need to move everything in the collection together. But that's implementation. It's not semantics. Now, the benefits of this is that there's no special behavior. It acts like any other collection from an optimization perspective, from a coding perspective. You don't have weird, surprising things like I made a gigabyte array of things and one of them stayed alive, so I'm still holding on to a gigabyte of memory. That would be highly surprising to a point of crashing, right? And it happens to be really easy to optimize for. So elements in the structure array are just regular elements. You can do anything to them because they are just regular objects. You can lock them, you can get identity hash codes. You can put them in other collections. You can take your array of objects and index it with 17 different hash maps. Try to do that with an array of things. And you can pass that content. It's just a regular object. You can take that member and give it to anything that expects a Java object. You could give it to log4j. You could give it to some old code that you don't like or don't know, but it does something. It's not going to break. It doesn't need to be recoded to deal with a new special thing. StructuredArray itself is also an object, and it's not special either. So this is all natural. It's this elegance that falls out of a decision where you immediately know it's right when you see all the things that get eliminated. Some other things about StructuredArray. This should say 2015. Or 2015, it'd be silly to think of an array with 2 to the 31st limit on length. That would be a fundamental mistake, almost as bad as building a language with no 64-bit integers in it. Oh, right, that's the previous talk. Not their fault, JavaScript just doesn't have one. I hope maybe ECMAScript will get one. Nested arrays are supported inherently. Multi-dimensional support is built in, so you can have structured arrays of structured arrays of structured arrays if you wanted. Non-leaf structured arrays are just element members, so you can have rows and columns and index the columns. And then there are things inside. Structured array is subclassable. This is a powerful feature, and we think it'll be the idiomatic way of using it. Yes, you could code to brackets if you want. If you like generics and a lot of them, no problem. But it's very convenient to subclass a generic type in a non-generic form, and it simplifies a lot of code. It certainly makes it much easier to do all the casting and checking and avoid all the needing to do suppressed warnings all over the place. Structured array is also not constructible. You can't make a structured array by newing it. You have to make it with a factory. Now that's a fundamental thing that we needed to do because of Java semantics. Java doesn't have a way of instantiating something of variable size except for a primitive array. New in Java is always a fixed size. New array is a variable size, but only of the basic primitive array types. This is a thing that we need to make that has a different in length depending on parameters to its constructor. And by the time we get to the constructor, it's too late. We're supposed to allocate this stuff. So we need a factory paradigm saying, factory, please make this for me, rather than a new and please construct in what I just allocated paradigm, which is why it has to be done with the factory. Now, has anybody noticed the contradiction in this slide yet? So the last two bullets here contradict each other. I'm saying that you cannot construct structured arrays, but they are subclassable. And you can't subclass something that doesn't have an exposed constructor. That's a basic requirement for subclassing. The super has to be constructible from wherever you're doing it. So how do we bridge that? Well, it turns out that we wrestled with this a lot because we wanted the qualities, but that's not how the semantics work. What we settled on is we need to make it impossible to construct a structured array. That's not the same as saying impossible to write something that tries to construct a structured array. You can write something equals new structured array. All implementations, including the vanilla one, will throw an exception if you try to run that code. So it'll never work anywhere, which means that we don't have to deal with it in a while. It'll fail in exactly the same way, everything, so it's okay. If you actually want a structured array, you will use a factory. And if you try to construct it directly, the base constructor will throw exceptions on you. We use something I call constructor magic that makes it safe to construct through the factory, including all the nice constructors for your subclasses, but not if you directly construct. And if you want to look at GitHub for how the trick works, you're welcome to it. It might be useful in other fields too. Now, optimized implementations of structured array would need to do something interesting here, and this is true for structured array in other forms too. You don't have to do this, you can just run the vanilla code, but it won't be any faster. It won't be slower, but it won't be faster. If you want to get the speed, you need to lay things out flat, and that means you need to start thinking of contained and container objects, a relationship between container and container. A container has regular objects, and the container itself is a regular object, so you can have hierarchies of this. And given a contained object, the JVM, not you, the JVM needs to be able to get from the contained to the container. The reason it needs to do that is if the garbage collector is moving things around, copying, compacting, whatever it's doing, and the first thing it ran into is a member object of a larger thing, it can't just pick that up and move it. It needs to move the whole thing together to retain the flatness. So if it gets to something that's contained, it needs to look for the outermost container and move that as one piece. The outermost live container, to be specific. Now, you don't have to deal with the details, the JVM writers like us need to, but that's basically the whole thing. That's the most we need from the runtime as far as new features or new behavior under the hood. This happens to be fairly simple to implement. We've been implementing it in Zing, a hard collector, the C4 collector, but also we've been building a proof of concept OpenJDK based with parallel GC doing this. And we've looked at what it takes to do CMS and G1, and none of them are highly complex. This doesn't introduce anything fundamental or different that the collector doesn't already seem to know how to do. There's certainly work there, but it's not trivial, but it's not highly complex and risky. So let's look at some more things about this. What are we going to get from optimized implementation? Well, once we lay things out in memory flat, because we can, streaming just happens. Streaming is simply a result of how you put things in memory, and if we put them in memory in a nice, flat, natural ways, like a structured array of objects and they're strided, then all streaming operations will simply happen as a stream. Hardware prefetchers will just do the work. No need for special optimizations. Now, dead reckoning does need some compiler interaction. And the reason for that is when we want to get to element 17, we don't look a reference up to get there, but we have to do an operation that looks like this. This is the actual math needed. So to get to address of element, we need to take the array address, add the body size of the array, and then multiply the index by the size of the element. That's how you get to the address of the element. In this statement, body size and element size may vary between different instances of the same structured array. Sorry, not structured array. So body size could be different because structured array could have subclasses. So different structured arrays, the subclasses could have a bit different body sizes. Element size could vary between two instances. I could have a structured array of point and a structured array of box. Those are two different element sizes. So these are not a dereference, but they are a data-dependent calculation of the final address. So what do we do about it? Well, element size and body size are not constant, but it turns out that they're susceptible to optimizations that we do in JVMs for other reasons. Not the same optimizations, but I'm using analogies here. Who here knows what class hierarchy analysis does? So that's a whole different JVM mechanics talk to talk about. So I'll do a quick thing on that, looking at time. Class hierarchy analysis is super powerful. It's why you don't have to do final methods. And you don't have to expose private fields. When you have a method that is the only implementer in the world, for example, I have a base class animal that has color. So animal get color gets the field color, private color. And then I have a dog and a cat and a bird. All of those don't override color. There's only one implementer. Class hierarchy analysis allows us to say, hey, in the world we know today, right now loaded into the JVM, there's only one implementer. So when I see that virtual call to get color that's supposed to look at my type and all that, I know there's only one, so I'll go straight to that one. If I load a class later that makes that assumption wrong, I'll throw away the code and recompile it. That's actually what happens. Okay, so when you load a class, you might de-optimize things that were done. And class hierarchy analysis is done when you load classes. And actually, when you load the class and when you make the assumption to begin with, is more likely. The loading is the invalidation. We can do a very similar thing here to say, yeah, body size is not constant, but is there a subclass of structured array? Of this structured array type that I'm looking at, structured array of point, let's say. And if there isn't, then I know exactly what the size is, and it doesn't change until a new class of subclasses it appears. It's a similar analysis. Now, the other implementation, the optimization at school, is an inline cache. What if I have in that world I gave you a chameleon? And a chameleon is this animal that sits on a branch, and the get color depends on the branch, so I need to override get color. No longer one implementer. You have to throw away that optimization. However, if the code is sitting in a dog kennel and all it sees is dogs, and never sees a chameleon, it actually could sit there and say, you know what, I've only seen dogs. I think I need to call the dog get color, which is animal get color, and I never see chameleons. It could speculatively say, if it's a dog, call that, which is much cheaper than figure out which method to call. In a similar way, element size fits in a similar thing, right? We could say, hey, this thing could have anything in it, but I've only seen points. So if the element type is point, then use point as size, otherwise do some slower thing. That replaces a data-dependent operation of getting the type with a control flow operation that speculates that something is right, and we'll have to reverse and basically mispredict the branch if it turns out to not see a point, which won't happen. These optimizations are common for other things. We believe they'll be common here too, and that's why dead reckoning should and we believe will work. There's a lot more detail to this I won't get into here. Quickly looking at the other forms. We have other things, struct and structs, and an array, a struct with an array at the end. Struct and struct is something we call intrinsic objects. Intrinsic in the English language meaning intrinsic to, not in what optimizers think is intrinsic. So object X is intrinsic to object Y. It's inside of it, created at the same time, it's a natural part of it, etc. For example, this is the syntax for declaring an endpoint in a line. It's a private final point. This syntax should be readable because it's not new, there's no language stuff. But there is an annotation saying this is intrinsic. And you initialize it with a factory that does an intrinsic object construct with it. This is as thin as we've gotten the spelling so far. There's some, you could get this thinner, but then you would need language changes. So this is as far as we think we can go right now without changing the language. So intrinsic objects are there, and that would allow us to lay them out within the object. An important thing to note is we put the object inside, but we will keep the reference field, and the reference field will point to the object. And the reason we need that is because there are all kinds of things in JVMs that unfortunately we have to deal with in a JVM. For example, final doesn't really mean final. You can override a final field and put something else in it. For example, every time you deserialize a class that has reference in it, you're probably doing that. First you make it, then you point it to something. And that means that if that happens, you may point to something that's not the one we picked, so we need to be able to follow the reference to the right place. Again, the speculation here is it doesn't happen, so when you get to the inner class, you go straight without dereferencing. But if somebody using reflection overrides finality of a field, we throw away the optimization and actually use the reference and just go as slow as regular Java does today. Anyway, that's the trick there. Structs with an array name are simple because we just create them as subclassable arrays. A subclassable array is a natural way to extend fields, and a subclassable anything is a natural way to add fields to a structure. And if we take an array, that's a way to represent that. We also have a reference array, so we can have a generic reference array. Structured array is already subclassable, so it already allows you to have a struct with an array of structs at the end. That's just the result of that. Now these forms together are composable, which gets interesting. So this is where you get to have turtles all the way down. You can have the heap, and inside the heap you can have a regular object. You can have a structured array of foo. And then you can have a structured array of foo as a member of that. And then you can have foo as a member of that. And inside foo we can have two intrinsic objects that are bar and doof, and in addition to other fields. And inside bar we can have another array of fixed size length that is intrinsic to bar. This entire thing can be flat in memory. And to show you what it looks like in example code, here's an array of octagons. It's a class, it's called octagons. But some classes, structured array of octagon. Makes it nice to deal with octagons. And then within octagon, we have an intrinsic array of 8 points, because it's an octagon, fixed length. And that's an intrinsic structured array of point elements. And then we can do the rest down there. Now the nice thing there is you look at the statement at the bottom, getting to point x of, coordinate x of point index of octagon y inside an array. And there's not a single required dereference here. And you can stream it. It's flat in memory. So that is simply math on the address octagons, rather than the other references. Now the nice thing is you can use them in natural iterators like this. You can iterate on octagons, iterate on points, and then go to get the things, and there's no memory access in iterators. These are all just math on octagons. Right? So even though you're iterating, you're just iterating math rather than walking memory. Okay, let's quickly look at status. Vanilla code is on GitHub, it works. We're still working on some spelling and looking for input, but we think it's fairly mature. Intrinsified implementations are being worked on for both Zing and OpenJDK. We will share them very soon, we think, trying to propose an OpenJDK project. That's the next step, an OpenJDK project. And the aim is to add object layout as a library, and only that, to some version of Java. Vanilla implementations will work fine, but if we look at this, since this will work on any JDK, what we're actually asking for in adding it to a Java spec is not to implement the optimization in the JVM. That can happen anytime later. We just want these classes in the namespace. Which means that if we mature them and we have the right semantics for the classes, we can just move them in and it'll just work with no change in the JVM. So we're just asking, here's some classes that work, can you move them into the namespace? That's the only actual change we'll be asking for. Once we get there, then we could go wild with everybody optimizing the code wall, and we will contribute optimizations to OpenJDK to do it, but we don't have to do it maturely and in time for some specific Java version to do that. So that's it. I think I'm on time. I don't know about questions. We probably don't have much room for those, but here's a slide for questions. And I do have a second talk today. If you liked my tone or my style, I'm talking about an LMAX case study of using our actual product Zing at the last talk of today in the sponsored talk slot. There's some links here, and do we have time for a question or two?
I think we have time for the 3 serious questions.
Okay, let's
three serious questions we have, so let's thank the speaker first.